Let's try to understand bias variance trade-off using an example. First of all, I would like to attribute the clevermachine.wordpress.com because this picture has been taken from that blog, and I definitely recommend you to check out that blog as I could find lots of interesting stuff there. So let's start with bias variance trade-off. So here fx is the function which we want to predict. And let's say g1x is the model that we use to predict fx. And so basically we train the model g1x on different datasets and plot those individual g1x using the thin red line, as you can see. So there are so many thin red lines here. And all those thin red lines are basically representing the regression line for the model g1x when it is trained on different datasets. And the thick red line here, this shows the average of those predictions for every data point x when g1x was trained on different data sets, whatever the average obtained for that data point. Basically mu is the value which is denoted by dark red line. So here we can see that the bias is very high because the difference between mu and f is very high. So mu is the dark red line. So here we can say that mu is here and f is the black line. So difference at many of the points is very high, and we are not able to learn the black line actually, and it's clearly the case of underfitting. But on the other hand, we can observe that variance is very low. So variance means that the difference between those thin red lines is not much. All thin red lines are very close to each other. And that's why we can say that the variance is very low. But this is not what we want, because it is not able to learn the true function fx represented by black line very well. Now let's see the second case. And this is the case of overfitting. So here, instead of linear regression, we use a polynomial regression of degree 10. So basically in our regression we include the regressors to be x square, x cube up to x raised to 10. So here we can see that the dark blue line, which is the basically mu, which is basically the average predicted output, is quite close to the actual output. So mu minus fx is close to 0. So basically blue line is overlapping black line. And this is the case of low bias. So here the bias is very low, but variance is very high. Variance means how close are the thin blue lines, which is the individual g10x when we fit it on different datasets. So when we fit our model on different datasets, how close those models are, and we can see that the variance is very high. So variance is high, as we can see that the blue lines are scattered all over the plot. They are not following same pattern. So it might be possible that you get a bad sample of the dataset and your prediction can be very wrong. Let's say if you get this line here, your prediction might vary with the actual value here by a lot of amount. So it is not good for a model to have high variance, and this is a case of overfitting, and we would not like our model to overfit. And an ideal case would be when we use a polynomial, let's say of degree 3. Here in this case, we can say that we have both a low bias and a low variance. Low bias because the average of all the thin green lines, which is the average prediction, the thick green line overlaps with the thick blue line very well. So bias is very low. In fact, I would say it's even lower than this case, because here the blue line is kind of going away from the red line in these cases. Like for such cases here, you can see that the black line is here, the blue line is here, the bias is quite high. For some points the bias is low, like here the bias is 0, but in general bias is low. But here the bias is very low. The solid green line is very close to the solid black line, and the variance is also very low because all the thin green lines are very close to each other, which means the variance is also low. So this is the ideal case which we want. So we want to select the parameters of the complexity of the model such that the average error, which is bias square plus variance, which is the average mean square error as we saw in the previous video, should be very low. So for example, here we can see that the average error is low when the degree of the polynomial that we are using to train the model is 3, and so this is the perfect model. So if we go beyond degree 3, the variance gets high. If we increase the complexity, variance gets high, and if we decrease the complexity, bias gets high. So if we go here, we can see that the bias is very high here. So we, at this point, the bias and variance are both low, and so that the pink color dotted line, which represents average mean square error, it's also the lowest at this point. And we can see that the test error is also lowest at this point of time when the degree of polynomial is 3. And the training error for the same case would be something like that. So training error would be something like, it would be lower than the test error. It would be quite low at this point. And so basically, I'm not plotting the actual training error, so this is the kind of training error we can expect. And as the model tends to overfit the data, the training error can go lower and lower, but the test error would go higher. So training error goes lower as we overfit the data, but the test error after this point goes higher. And since we care about generalizability, we care about test error more than the training error, and hence the ideal model parameter for this case would be a polynomial of degree 3. So the bias variance trade-off is also understood in terms of bullseye diagram. So let's say the smaller circle here, this circle here, represents that the model has low bias, that is, it is very close to the target. The model is very close to the target that we want, and the closer the target, the lower the bias. So a high bias and a high variance situation would be that the first time we train the model, we get our model very away from the target. The second time we train the model, we again get a model which is very away from the target. Third time we train the model, we again get a model which is very away from the target. And so this is the kind of an example of high bias and high variance, where even the model is not consistent. We are getting a scattered model every time we train our model on different datasets, as well as we are getting our model which is away from the target. A high bias and a low variance case would be when consistently our model is away from the target, but the model is consistent. The model, every time we train the model on different datasets, we are getting all the models which are very close to each other. So this would be the case for high bias and low variance. On the other hand, a low bias and high variance case would be when the model is close to the target, but it's not consistent. Sometimes you get a model here, sometimes you get a here, sometimes you get here. So it's scattered, but it's close to the target. And what we aim for is a model which has both a low bias and low variance. So basically a model which is close to the target and is very consistent. It's not scattered here and there. So this is what we actually want, and this is the ideal case. So I hope by this video it's quite clear to you the bias variance trade-off as we decrease or increase the complexity of the model. See you in next video.